Welcome, LiDAR lovers, and welcome to this 8th episode of LightConversations. I'm joined by James Portman. Welcome, James.
Hey, Phil. Nice to see you again.
Yes.
I'm looking forward to this one.
Yeah, well, it's our brand new studio, and so please forgive the shadows, and we're still working things out, but thank you for joining us. Today's an interesting topic. We're discussing optics and lenses. And this is where we left off last time, as the laser emits from the sensor, we then move into the world of optics and LiDAR. So I'm going to hand over to you, James. Are there maybe any initial comments that you'd like to make as we move into this world of, we've covered the electronics, we've covered the conversion of electrons into photons, and now we hit the optics. Where does this leave us now?
So I guess if you're a petrol head and you like cars, you want to know where the performance comes from, right?
Yeah.
And there are definitely a number of elements in any machine and in any device which make the thing work, that really give it its capability. And it turns out that in LiDAR systems, it's the optics themselves that do it.
Right.
People think it's the laser and it's the detector and it's the signal processing and everything else. But it turns out that you can resolve a lot of evils if you can get the optics right. The optics provide, it's like the equivalent of the American muscle car. It gives it the torque.
Right.
It gives it that superpower.
It's the gearbox in the equation.
It is. And what's interesting about it is there's almost no limit to it.
Yeah.
In other words, if you just put bigger and bigger optics onto a LiDAR system, you get better and better performance.
Right.
Now, this is not true in the realm of, let's say, amplification. Because if you're amplifying a signal, you're also amplifying noise. So there's a limit beyond which it doesn't help. Your signal-to-noise ratio becomes limited, and so more amplification doesn't help.
Yes.
But what optics does for you is it helps you collect more signal without necessarily collecting more noise.
Right.
And that means if you have bigger lenses or bigger systems, surprise, surprise, you get better performance out of it.
So let's talk about that. I've always had photography as a hobby. I love it, and your aperture size on a lens is so absolutely critical. And that's why a f1.4 lens would always be better than a f3.5. You're able to open up the lens a lot wider, which allows in a lot more light. Now, of course, from a LiDAR perspective, we're speaking of the exact opposite, because we're transmitting light, but we're also receiving. One of the challenges we spoke about before on the previous episode 7 was around eye safety. And, in an ideal world, we'd have LiDARs with diameters this size, which is probably what they use to the moon. But one of the challenges that we have with micro LiDAR devices at LightWare is around building something that's small enough to go onto a drone. So what are the considerations from an optics perspective when you look at the power of the beam and the ability to be able to receive that light with regards to the diameter of the lens?
So it turns out that the best way of looking at it is as two completely different kinds of problem. The first problem is, how do you get the light out? In other words, how do you go from an emitting device, the laser, and project the beam as far away as you can in the most concentrated form you can without exceeding the eye safety limits.
Yes.
So think of that as problem number one.
Right.
Problem number two is picking up a few photons that come back, collecting them all together and focusing them on your detector. Now, surprisingly, problem number one is an imaging problem. So rather like your camera analogy, what you're actually trying to do is you're trying to create the most uniform outgoing beam that you can.
Right.
You don't want hot spots in the beam. You don't want the beam spreading out and diffusing. Okay. You don't want a jumble coming out. What you want is a nice clean image of the laser being projected. That is the ideal solution.
Okay.
Now, of course, as you go to smaller lenses, it gets harder and harder to do that, because you get more optical distortion, and you have to be a little bit more careful about it.
And it's obviously having a uniform beam, but at a series of distances.
Correct.
So it's probably it's a lot easier to do, to say, well, we're working at 3 feet and give me a uniform beam, but to do the same uniformity and achieve that at 3 feet as 300 feet must be a huge challenge from a design perspective.
Yes, because what you're trying to do is you're trying to achieve ideal collimation, as they call it, and collimation is the degree of parallelness of a beam.
Right.
So on the outgoing side, you're taking, if you're using a semiconductor laser, for example, it produces a horrific beam pattern. It is kind of like a distorted ellipse coming coming out in a very wide cone.
Right.
And you now need to collimate this into a perfectly uniform parallel beam. In many cases, it requires multiple optical elements to get this collimation to be efficient.
Yes.
But then you have a trade-off in doing that, in that the product that you manufacture could become heavier or larger and more expensive, of course.
Yes.
And then don't forget the manufacturing side. The moment you start working with multiple elements, your manufacturing processes can become a lot more expensive and a lot more complicated.
Which is like a camera lens. You've got 8, 9, 10, 11, 12 elements all in series to be able to shift the light and to move the light in the right sort of parallel direction to be able to focus and zoom and all of that. So
now you do have one nice advantage in a laser system, of course, and that is that you're dealing with monochromatic light.
Yes.
Which means your lens equations and your calculations become a lot simpler. You only have to worry about one wavelength.
Yes.
What makes camera systems particularly difficult is, of course, you're dealing with multiple wavelengths, multiple colors, and therefore chromatic aberration becomes a major problem in your lens design.
Okay.
With a laser, you actually don't even have to worry about chromatic aberration at all, which is terrific. So you can come up with simpler lens elements.
Okay.
That having been said, of course, you're dealing with this distorted beam of laser light, and you now have to correct for these distortions. So you win on the one hand, but you lose on the other hand.
Yes.
So what I found fascinating the first time I built a LiDAR system was that understanding how to get this collimated laser beam was pretty straightforward. You know, you can manage it, and you can buy optical elements that'll do the job. What I didn't realize is on the return side, it's a completely different problem.
Right.
The reason is that the only thing you care about on the return side is catching photons, catching the photons that you want. You don't care, for example, about image distortion, because the beam that comes back to you is just a wash, like a rainfall of photons just coming back.
Right.
All you care about is getting those things down to a detector.
Yes.
So you only have to focus it to a spot that is the size of your detector. And your detector could be, let's say, 0.5 millimeter across or something like that. As long as you can get those photons onto that 0.5 millimeter element, that's it, you're done. Now, in other words, you can almost treat the optical system as an energy gathering device, not an imaging device. Now, this is really important.
So no consideration on focus or depth of field or...
Well, they do play a role, but they play a secondary role.
Right.
What's more important to you is just collecting these photons.
Yes.
The parallel comes from the world of astronomy. In astronomy, you have two types of telescopes. You have telescopes that take photographs of galaxies far away, and you're looking for precision and detail in the little spots which represent the stars, and everything must be deeply focused in order to achieve that. But you get a different type of telescope where you look at the spectrum of the device that's far away. In other words, you care what color components are in there, but you don't care how sharp the image is.
Right.
So you would generally focus onto a spectrograph.
Yes.
And what that...
Which is collecting photons at different wavelengths.
Correct.
And
but all it cares about is how many photons have you got. It doesn't care whether they're perfectly in focus or anything else like that.
Yeah.
And in a way, it's that spectrographic analogy that is more appropriate in a LiDAR detection system.
Right.
So that means you can use big optics on the receiver side, and it just collects more and more light. In fact, the range of your LiDAR device is directly proportional to the diameter of your receiver lens. As simple as that.
I was just going to ask the question because generally on our current micro LiDAR devices, we have sender and receiver lenses of the same diameter. You know, have you considered different designs where, you know, you look at different diameters on the sender and the receiver?
Absolutely. Yeah. In fact, normally that is the case. They're not normally the same size at all.
Okay.
The reason why we do it is because, remember, we're trading off a lot of engineering parameters here. We're not only necessarily trading off the ability of the receiver to detect the light or the ability of the laser to collimate the light.
Yeah.
We are looking at manufacturing cost. We are looking at assembling processes. We are looking at material specifications, mechanical stabilities. Numerous different factors come to play. And it is easy to say we will over-torque the engine. In other words, we'll put a supercharger on our engine, and then it breaks the gearbox, or it breaks the axle, or it breaks something else. It's the same kind of analogy with LiDAR. If you overpower one element, you have to be careful that you don't lose that performance somewhere else.
Yes.
So for instance, if you do use a large lens and you have a decent focal length on it and you get a beautiful collection of photons, but you get thermal distortion, in the system that is holding the lens in place and holding the detector in place, then guess what? As the temperature changes, your performance goes all over the place. So you then end up using machined Inconel or something like that in order to create a stable platform on which you're building this thing, which then puts the price up and puts the weight up and it gets bigger and heavier and so on. So it's more of a coincidence than anything else that we've ended up with similar sized optics on the laser and the receiver, very much engineering compromises. But it doesn't have to be like that.
Okay, interesting. Let's just consider the different kinds of lenses that we can use. Maybe talk to us just around the lens characteristics. I know that there are different kinds of lenses that we can use. And maybe just if you'll cover the different kinds of coatings as well that we use on the lenses and the purpose of those.
So the coatings is the easier one. Obviously you want lenses to be efficient, and if a lens either absorbs or reflects some of the light that goes through it, generally at the surface of the lens, then you will lose performance from the lens. And a typical uncoated lens, if you like, 90 to 95% transmission. Well, it depends. If you get a really cheap lens, maybe it's only 80% transmission. But once you coat it, you can be up to 98% or even higher than that. So that squeezes a bit more blood out of the stone for you and helps you not to lose things. But there's another reason for coating a lens, of course, and that is that the coatings tend to be very hard. So it improves the scratch resistance of the lens so that it's easier to handle. Also doesn't necessarily show up fingerprints as badly and that kind of thing.
So what about backscatter and, does the coating help manage any of that?
Yeah, it's amazing how many people we have discussions with about this concept of backscatter because LiDAR systems are extremely sensitive to backscatter. For instance,
maybe just explain the concept. Sorry, just before we get down there.
Suppose you shine a laser beam onto a piece of glass or a window or something like that. Most of the light will go through, but some of it's going to come back. Now, the issue you have with what comes back is that in something like a camera, this could show up as maybe a ghost image, because you get multiple reflections within the lens system. In the case of the LiDAR, it shows up as a ghost return signal. And that return signal can be very close if your lenses themselves are scattering light and the detector picks up the light from the laser. Of course, it shows up
within the system itself.
Within the system itself, So there's really only one way to handle backscatter really effectively, because you're always going to get a small percentage of light coming off the lenses, and that is you have to isolate the lenses. In other words, the lenses must never be able to see each other. There must be no optical path between them. And I do know that a lot of people try and make fancy systems with combinations of mirrors and various other things. And if you look closely, you'll always find there's a leakage path there somewhere. And then they're very surprised when they discover that it keeps reading this very short signal because, of course, there's crosstalk there. That having been said, of course, the question then is, so what is the ideal lens configuration? You mentioned to use multiple types of lenses. Well, again, you have to treat it as two different problems. The types of lens configuration that works best for the laser will not be the ideal lens configuration for the receiver. So in the case of the laser, you're dealing with this horrible distorted laser beam. As I say, it comes out as an elliptical shape, but with can be as much as a 10-to-1 aspect ratio on that ellipse. It's amazingly bad. So what you often tend to do there is not use the conventional lens that you would see in a magnifying glass, which has got a spherical surface.
Convex surface. And
what you would do is you would use two cylindrical lenses. And what happens is one of the lenses will have a focal length which deals with the one axis, what's called the fast axis. The other one will deal with the slow axis or the wider axis. And you can get it's almost like having to deal with two focal points coming from one source. And that is the way to get the best collimated beam out of one of these types of laser diodes.
And it's distorting an imperfect emission into the best column that you can.
That's exactly what it is. So, that's a nice ideal solution. There are other ways of doing it, of course, and that is that you could ignore the rest of the pattern that's coming out and just use the bit in the very middle. And then you can use a conventional lens, but you would be wasting an enormous amount of energy coming out of the laser. So
which then comes back to eye safety again if you're only using a portion and having to emit more. That's interesting. Thanks, James. Let's circle back to the receiver. I think we've got a good idea on the distortion of the emission, but maybe talk to us on the complicated side of the equation. What happens with the receiver?
So you obviously want to have a large lens on the receiver so that you can capture more photons. But it turns out that if you go very large on the lens, inevitably the focal length of the lens will get bigger. Yeah. So even if you've got an f1 lens or an f1.5 or something like that, the whole system gets bigger and bigger and bigger. Yeah. And as I mentioned before, bigger systems tend to be less stable. So you end up spending a lot of money machining things to make them more rigid. Yeah. So what you often try and do on the receiver side is you try and improve the efficiency of the lens system as well. Now this can be done by cutting out on things like spherical aberration. Now what happens with spherical aberration as opposed to chromatic aberration is that spherical aberration prevents the focal spot from being nicely confined. Now we don't necessarily need a perfect focal spot because as I've said, you've just got to get it onto the detector.
Yes.
But when your lens gets big, that focal spot can be very fuzzy. Right. And it can be fuzzier than the size of your detector. Right. So what you can do is you can use things like doublets, which are lenses glued together, made of different materials and with different curvatures.
Oh, right.
And you can, because you're operating at one wavelength, you can create an almost perfect lens like that, which gives you the sharpest focal spot.
Yes.
So now what you can do is you can have a well-collimated, when I say well-collimated, a well-focused beam coming back from the outside world. And it turns out if you can make the focal length a little bit longer and a little bit longer, the field of view of the lens gets narrower.
Yes.
Now, this is where you get something for nothing, because you have a big lens which is collecting a lot of photons, but you have a narrower and narrower field of view, which means you're collecting less background light.
Right.
So it turns out the ideal lens configuration for a long-range LiDAR device is a doublet configuration, relatively large size, but with a long focal length. You get fantastic performance.
But I mean, if you think about our smallest SF000 micro LiDAR, I mean, you know, the width of that device is a thumbnail.
Yeah.
There's not a lot to work with there. You know, if you're thinking about kind of focus points and focal length behind the lens. Yeah. So that must take some fancy footwork in terms of the calibration of those lenses to the receivers and managing those points. How does one ensure that, because I do know that these sensors can take a hammering. Yeah. You know, there are unbelievable examples of where these sensors work under very, very harsh conditions of vibration and being, I mean, we don't recommend you drop them, but, you know, I mean, on UAVs and UGVs and all sorts of craft.
And they get dirty, of course.
Yeah.
You know,
well, that's my next topic I'd like to talk about. But how do you ensure the stability of that lens system within such fine tolerance?
Yeah, and again, I think this always begins to open a new avenue of understanding here, because what I've been describing up to this point has been very much the theory behind lenses, what makes lenses work best. Once you transition from pure theory to engineering, things get a lot more complicated. Yeah. So yes, you can put a beautiful coating on your lens and you can guarantee to get 99% transmission. You can correct for your spherical distortion, spherical aberration. You can get great focal lengths, excellent signal to noise ratio, and then somebody flies their drone through a cloud of dust and things like that, and you end up with 50% of the lens covered in dirt.
Right.
Now the product must still work under those conditions. You must get almost no loss of performance. How do you do that?
Yes.
So often it turns out that the ideal solution is not necessarily advantageous in the non-ideal world in which we have to operate. So we come back to what goes into the design of a product then. The answer is, I'd love to have large lenses with large focal lengths, but we can't. So we have to go for much smaller lenses with much shorter focal lengths. I'd love to have an outgoing laser beam that is perfectly collimated, but it turns out that you can't at the scale that we're operating in. So we have to accept the fact that we get some beam divergence, and that's built into the design. We must accept the fact that the coatings on our lenses can still get covered in dirt, so we're going to lose half the signal or even 80% of the signal on some bad days. Balancing all of these out and being able to come up with a complete working system that takes every single one of these parameters into account takes a long time, I have to be perfectly honest. There's a lot of empirical testing that's required.
Yes.
You can run it through the optical modeling programs that you get, and you can see what happens. But when the customer gets into the real world, and the customer says, but wait a minute, my target is not a uniform target. My target is a rough target. That the air transmission is not 100%, it's raining. That the lenses are covered in dirt. Oh, and by the way, You've made a beautifully collimated system that's designed to work perfectly at 100 meters, but I'm going to be 5 centimeters away.
Yeah.
Now, how does it work?
Yes.
Because, of course, now you're no longer operating in the far field, you're operating in the near field, so everything's out of focus. So all the wonderful calculations that you did, you can throw them out the window, and start all over again.
Right.
And such is the delight of designing LiDAR systems, especially small ones. They get to be very, very difficult.
A lot more complicated. Yeah. Last question. I was posed the question, and I do know that we've recently, in the last year, switched from glass lenses. And I know that you are now favoring acrylic in a lot of the designs. We've had in-depth conversations with many customers on, the performance and how they found them. I think this perception exists out there that, glass has got to be better, which the tests have shown is not true. So maybe if you can share some ideas on, why you've chosen acrylic over glass. I know that you've done a number of tests in terms of abrasion, and so just tell us about your decision on acrylic and how that's helped us to keep designing the world's smallest micro LiDAR devices.
And lightest, of course, because acrylic is lighter for a starting point. Yes. Look, the drive towards acrylic is very simple: safety. If you're going to operate a device that has the potential of, let's say if it's a drone, it's going to crash into something, or if it's an unmanned ground vehicle, it could run into a lamppost or something like that. The possibility of crashing is always there. So ideally what you want to do is you want to design a product that's inherently safe.
Yes.
So that means you can't spray glass everywhere, and you want to make sure that the failure modes are well understood. Now, the problem with glass is that glass is very difficult to analyze from a failure mode perspective because it tends to fracture, shatter, shear, break up in very unpredictable ways. Acrylic is far more ductile.
Yes.
And because it's ductile, it tends to fail in a much more gentle way and doesn't break up into lots of little pieces, for example.
Right.
So the reason for having acrylic is very strong. From an optical performance point of view, acrylic does not give you the identical performance to glass. It's very hard to match them one-to-one. Fortunately, the difference is relatively small, 5%, 10%, something like that, depending on how much money you spend on them. So we are talking about a marginal difference in performance.
Yeah.
The interesting thing, however, is that when you look at it in the context of the entire product, as we were describing just now, the real-world conditions and so on, turns out that 5% or 10% is not relevant at all, because you're never using your glass lenses at optimal performance point anyway. So you're never getting the best performance out of the glass. So on paper, yes, it may look better. But it turns out that when you're flying over a tree on a windy day, doing a search and rescue operation.
In the rain,
okay, a loss of 5 or 10% of performance on the acrylic is much less of a problem than accidentally dropping a drone on somebody's head, which is much more of an issue.
Right, okay. Great. Well, thank you very much, James. I enjoyed the conversation. Learned a lot about optics. I would like to invite you to our next discussion, which we're starting a new channel called Light Experiments, and we're going to be working with some team members from the engineering team on running little LiDAR experiments. So please join us just for a quick little conversation on our next experiment. And our first experiment within that channel will be around the how dirty can a LiDAR lens get? What kind of grub and grime you can afford to have on your LiDAR lens before it stops performing? So
super stuff.
Great. Thank you very much. Thanks for watching.